Hello and welcome to part 2 on classical polarization. In this lesson we will talk about Jones matrices and interferometers, and I will also present all the problems for this chapter. First, we have Jones vectors. In the last video we talked about how the electromagnetic field can have polarization, which is the orientation of the electric fields in the electromagnetic wave that are transverse to the propagation direction. In this, we like to define the x-hat direction, and y-hat direction as corresponding to the horizontal polarization direction and the vertical polarization direction. In doing this, you can construct any other polarization as a linear combination of this basis. In fact, you actually see that if you have these as your bases, or as your basis, then you can construct all of the other polarizations out of it. And these are the actual matrix representations of the vectors. However, optical elements operate on polarization, and matrices operate on vectors, and you have Jones vectors representing polarization, so it makes sense to have matrices represent optical elements. And these are called Jones matrices. And here you can express all the other Jones matrices in these forms. This is the notation, these are the actual matrices, and this is what they represent, the optical elements they represent. Suppose you have a polarization, an initial polarization, which then passes through n optical elements, so it could go through n different things. Then the Jones representation of this would just be the initial polarization operated on first by the first element it passes through, then the second, up to the n. And here, ordering does matter, because it's matrix multiplication. And if you've taken any linear algebra class, you'll know that matrix multiplication in general does depend on the order of multiplication. And here it's the same. The physical system, if something goes through a quarter wave plate and then goes through a polarizer, it's not the same as it going through the polarizer and then going through a quarter wave plate. So here's an example of a polarization interferometer. In this one you have a horizontal vertical polarizer that is polarizing or separating out the polarizations from this 45-degree polarized beam. And then it is recombined right here. However, you'll notice that it's no longer 45. You have a phase shift between these two that is garnered throughout this material. And so you actually end up with it not being 45 anymore, but you have two separate, the vertical and then the horizontal polarization that are separated by a phase shift. Mathematically, one would think that both components go through and then end back up. And so you'd think that it would just be the unit matrix that represents this, or the identity matrix that represents this. However, mathematically, to account for that phase shift, you actually have to account for the phase shift over the horizontal polarization here. And so you don't get the identity matrix anymore, and you have this Euler formula up here accounting for that phase shift phi. You'll notice, however, that the path length for the horizontal polarization is much different than the path length for the vertical polarization, and so in general this is not necessarily a coherent structure, meaning that if you have a very, very short pulse length of laser, then the vertical polarization is going to hit this point much before the horizontal polarization hits this point, because it has a shorter distance to travel. And so because of this, this representation is only really effective if you have a continuous light source. To get around this fact, we have this setup where there is a half wave plate between them so that it switches the polarizations between the two light beams, and then rotates this polarizer at an angle proportional to phi to recombine these beams over the same path length. And here's another interferometer, which is given by this more complicated Jones matrix, and you can see how you actually work out the new polarization, it's just the polarization times Jones. And you'll notice that I don't have this as a unit vector here, and that is because the polarization, if you're just accounting for this polarization right here, it doesn't necessarily conserve intensity, which you can see this as the intensity out would be proportional to the intensity in times the value of the magnitude of the polarization, of the new polarization. And so you actually end up with this angle phi dependence of the phase shift. In terms of problems, this is the first half of problems. There's not much more for me to say. Just work on these if you want. And then there are these other two problems. Thank you for watching. This was a relatively short one, and if you have any questions, please ask them in the comments. I would love to clarify any things that I was ambiguous on or maybe didn't explain the best. Thank you again for watching. Bye.